Okay, we're going to proceed with part 2 of Voila proofs with iteratively inscribed similar triangles. And in this section we're going to do a couple of standard proofs from elementary geometry or not so elementary geometry. But these proofs give a new insight and also I think they're visually appealing. So let's get started. Okay, quite possibly you're familiar with the centroid theorem. Recall that the centroid is the intersection of the three medians of the triangle. Median being the line from a vertex of the triangle to the midpoint of the opposite side. So in this picture in the slide you can see three medians. The green median vertex from one vertex to the midpoint of the opposite side, red and blue, all give medians. So the centroid says that the three medians of the triangle actually do meet at a single point. Of course it looks that way, but it's actually a mathematical fact. And the intersection of these three medians is called the centroid. The other part of the centroid theorem is that the centroid divides each median in the ratio of 2 to 1, which also looks visually clear. Look at the green, red, and blue medians. It looks like that little triangle in the middle divides them into the ratio 2 to 1. So, but appearances can be deceiving. We need a mathematical proof. So let's go ahead with a proof. This proof is kind of a puzzle proof. It's something that you could do with students. They could make these puzzle pieces that I'm going to describe to you. So here's a puzzle piece. Take a triangle, any triangle. Mark off the midpoints of the sides here, here, and here. Then you can create a triangle by connecting these midpoints. And then just cut out that triangle, leaving a hole. Okay. After you've done that, then go ahead and place your ruler from vertex to midpoint and draw the line from vertex to midpoint. Now, of course, there's a hole there, so it won't go all the way through. So do that with each vertex and each midpoint. Vertex, midpoint, draw the line. The hole prevents it from going all the way through. And similarly with a third. Vertex, midpoint, draw the line here. Okay. So that's how you create one of these puzzle pieces. Okay. Now let me make a similar puzzle piece half the size of the original. And then another puzzle piece 1/4 the size of the original. Then 1/8 the size of the original. And so on down the line. Of course, you're going to be limited very quickly to how many puzzle pieces you can make. Notice how I've colored the puzzle pieces. The half-size puzzle piece uses light colors. The 1/4 size uses the original colors, and so on. Okay. All right, so the proof of the centroid theorem simply involves assembling the puzzle pieces. Start with the first piece, put in the second piece, third piece, fourth piece, and so on. All right, so what does this show? I just put together some puzzle pieces, but what does it show? Now look at how the lines are lining up. Take a minute, maybe you can pause the video and try to think about what this is actually showing. Well, if you look at the blues all seem to line up. The reds all seem to line up. The greens all seem to line up. And they all seem to be they all are touching that little triangle in the middle. That little triangle is getting smaller and smaller. Eventually, they're going to go in and touch a single point. So all those three lines, which happen to be the three medians, seem to meet at a single point. Also, if you think about how I created the puzzle pieces, the dark-colored segments are all twice as long as corresponding light-colored segments. Look at the puzzle pieces up top. The first puzzle piece has a dark blue segment, which is twice as long as the light blue segment in the second puzzle piece. Third puzzle piece has a dark blue segment twice as long as the fourth puzzle piece. So if I add up all the dark blue segments, I'll get a length twice the length of the light blue segments. The same with green, same with red. Okay, so it looks like I've gotten the centroid theorem. I both have the medians converging to a single point, and I have the median being broken into the ratio of 2 to 1. Okay, so looks like a very elegant. Now, of course, things aren't always as easy as they appear. So let's fill in some details. Just to remind you of the process, here we go. We put the puzzle pieces in. Now, the thing is that in geometrical figures, sometimes things look like they're true, which may not actually be true. So I said that the triangles fit in the holes, and if you make them, they will. But can you prove they really do? Maybe they don't really fit, they just fit sort of. Can you prove that they actually do fit in the holes when I put those puzzle pieces together? Can you prove that the same colored segments actually do line up, or does it just look like it? And how do we know that all the segments really do meet at a point? Well, think about these three, and it's not too difficult to answer all of these objections. In fact, you can use similarity arguments to show that the hole in the middle of the biggest puzzle piece is exactly the same size and shape as the second puzzle piece. You can also use similarity and parallelism arguments to show that the same colored segments line up. When we created the puzzle pieces, if you look back at the previous slide, when we created the puzzle pieces, the similar colored segments were certainly parallel because I just scaled down the same triangle by half. Everything was scaled down by half. I didn't change the direction. I only changed the size. Okay. Then when I flipped the inner puzzle piece 180 degrees to put it inside the bigger puzzle piece, when you flip something 180 degrees, you don't change the direction of any straight segments in the figure. For instance, that light blue segment, when I flip it 180 degrees, it's still the same direction. It will still line up. Okay, so because the only operations I'm using is scaling down and flipping, I'm not changing any of the directions of the colored segments. All the colored segments are the same direction. They all line up. Therefore, when I assemble them, they must lie on the same line. So the blue, green, and red actually do represent three straight lines. All right, now how do we know the segments all meet at a point? Now here's where it gets interesting. If you really want to be rigorous, you have to use something like the completeness property. You have some Cauchy sequences here. The dark blue segments, the endpoints of the dark blue segments form a Cauchy sequence. The endpoints of the light blue segments form a Cauchy sequence. Same with the red, same with the green. We've actually got 6 Cauchy sequences. Every Cauchy sequence in the plane must converge. You can prove by contradiction that they must be converged to the same point. Okay, so we have 6 Cauchy sequences converging to the same point. And this point actually must be on each of these lines because a line is closed and it contains all its limit points. So, as I said, these are technical details which are really necessary for rigorous proof. That makes it kind of hard to prove completely rigorously, but I still think that there's some insight and benefit showing this to more elementary students. It's a very, I think it's a very visually appealing proof. All right, here's a summary of the proof on a single slide for your viewing pleasure. Okay, now let's go one step further. There's something called the Euler segment. A triangle doesn't just have a centroid, it has other centers of importance. One is called the circumcenter, which is the intersection of the perpendicular bisectors of the triangle. One is called the orthocenter, which is the intersection of the altitudes of the triangle. Now, Euler showed that these 3 points, these 3 centers, are actually collinear. He also showed that the centroid is in between the orthocenter and circumcenter, and it divides the segment in the ratio of 2 to 1. So here we see this 2 to 1 again, kind of reminiscent of what we've seen before. All right, now let's see if we can modify our previous construction to get this stronger result. So here's another puzzle piece. All I've done is taken a triangle, and I've drawn the 3 altitudes, and they intersect at a point. Now, I'm not going to prove that the 3 altitudes intersect at a point. You can prove that by other methods, other elementary geometric methods. All right, here's the same similar puzzle piece, half size, another puzzle piece, half size, and so on. All right, now before I assemble these, I'm going to make a complex puzzle piece. I'm going to make a duplicate of the second puzzle piece and place it inside the first, and do that so on. So I have all these puzzle pieces, but they're a little more complex. I think it makes it easier to see what's going on. Okay, so now I'm going to assemble. Now here I don't have holes, so I can't place the triangles inside the triangles, but I just can place them on top. I can place the second puzzle piece on top so it lines up with a blue triangle in the first puzzle piece. All right, now notice that the blue lines are actually perpendicular bisectors for the larger triangle, because each blue line is perpendicular to its corresponding side, and it passes through the midpoint of that side. So in a sneaky way, we've come up with the circumcenter of the large triangle. The blue point is the circumcenter of the largest triangle. Okay, now I fit the second puzzle piece inside. I'm going to fit the third puzzle piece inside, and I could keep going. I think that's all I did. But look at the 3 points, red, blue, orange, green. What does it look like they're doing? Well, it looks like they're lining up. Okay. Okay, it looks like all of the points, now I could keep going. I've only shown 4 points. 1, 2, 3, 4. But I could keep going. And of course, these points would get closer and closer together. But it sure looks like, and we'll see that it's true, these points all lie on a single segment. Now this segment must contain the centroid because the triangles shrink down to the centroid. Okay, so what we have is that the orthocenter and the circumcenter, we have a segment, and we have the centroid lying in between orthocenter and circumcenter on the same segment. All right, pretty neat. So by considering the lengths of the segments, the centroid splits the segment as 2 to 1. All right. This may be not 100% immediate to see, but it's not that difficult if you point out what you need. All right, think about the distance from the red point to the point of convergence of all the triangles. How am I going to get that distance from the red point here, to the circumcenter, which to the centroid, which is somewhere in here in that inner triangle? Well, if you think about it, that distance is going to be equal. It's not as big as the distance from red to blue. If I take the distance from red to blue, that's from here to here. All right. How about the distance from red to orange? Well, I'd have to take the distance from red to blue and then subtract the distance from blue to orange. And that's going to give me the distance from red to orange. Okay, so I've taken red to blue minus red to orange. Now suppose I want to get red to green. Well, then I'm going to have to add back the distance from orange to green. So if you see what's happening, I'm alternately adding and subtracting the lengths of these segments. Add, subtract, add, subtract. So from red to the centroid, it's going to be red to blue, subtract red to orange, add red, orange to green, and so on back and forth. Okay, we've got an alternating sequence, plus minus, of segment lengths. Now what about the distance from blue to the centroid? Well, it's really quite a similar situation. To get from blue to the centroid, I go from blue to orange, then subtract orange to green, then add green to the next one, and so on, so on, so on. If you think about that sequence of segments, each segment is exactly half the length of the segment in the sequence involved from the red to the centroid. So since each segment's half the length, the sum's going to be half, and that's why the centroid splits the segment from red to blue into the ratio of 2 to 1. The centroid's half as far from the blue as it is from the red. Now, of course, there are some technical details, as there were in the centroid proof. Okay, let me just put in my puzzle pieces to remind you how it goes. So what do we really need to show formally in order to show that this proof actually does work? Can we prove that the points red, blue, orange, and so on all lie on the same line? Can we prove the centroid lies on that line segment? And can we prove that the ratio of distances is 2 to 1? All right, and the proofs of these 3 parts is similar to the proofs in the centroid proof. We have parallel segments passing through similar points, through identical points. We have Cauchy sequence, and we have length. I already mentioned the length proof. So to close, there's a summary of the Euler segment proof in a nutshell.